We now move on to the second part of Lesson 5, that is hypothesis testing for two populations. And these are the topics that we're going to be going through. This part of the lesson is going to be split up into smaller components because in two cases we're going to be looking at generating output using SPSS. So first of all, we'll look at the test for difference between means of related populations. So as well as being able to make inference about the difference between population parameters using confidence intervals, we might also be interested in testing. And we already demonstrated that when we found confidence intervals, we could actually perform a test where we have a two-tailed alternative. So we're going to be looking at difference between two populations for means, variances, and proportions. So first of all, let's have a look at hypothesis testing for the difference between means of related populations. Now, if we assume that this difference, x1 minus x2, is normally distributed, then the sampling distribution of the sample difference, d bar, is approximately normal. We already came across that when we're dealing with confidence interval estimators for the difference between means of related populations. The mu d and sigma d defined as we did before, the mean and standard deviation of the difference respectively in terms of the populations, and more often than not sigma d is unknown, so that being the case, then the standard Adams mean difference follows a t-distribution. So we've come across that previously as well. So we could set up the hypotheses like this. So we have our mu d being equal to some unknown value, which we called capital D naught, against an alternative, which could be a two-tailed alternative or one-tailed alternative. There's a test statistic, follows a t-distribution, so the critical value approach would be to compare the test statistic to the t-critical values, or we could use the p-value approach. So the mechanics are exactly the same as before, except we're looking at something different now. Then in this case, the difference between means of related populations. So if we were looking at a two-tailed alternative, then that would be these would be the regions of rejection, right? These tail areas. If we have a one-tailed alternative greater than, then that's the region of rejection, the upper tail area. And if we have a one tail lower than, then the region of rejection is this lower tail area. So let's have a look at an example. This is example 5.4 in the unit book. We're going to use SPSS to generate the output before we can go on and perform the test of hypotheses. So what we're looking at here are pre-training and post-training scores of 40 individuals in this company to look at their computer skills. So there's training provided. What are their skills before training? What are their skills after training? So we have scores, post-training and pre-training and post-training scores, and we want to test if there's a difference. So here are the questions that have to be answered. Using a 5% level of significance, do the given sample data support the claim that the organization's training program is increasing new employees' working knowledge of computing? We can also obtain a 95% confidence interval for the mean of the difference between post and pre-training scores, and we will also perform some diagnostic checks. So let's move on to generating this output in SPSS. So here is the data set. So we've got before and after scores for each of the employees. So to generate the output for the paired samples t-test, we go to Analyze, Compare Means, Paired Sample t-tests. Now we need to put these into the variables. These are paired variables. So we'll go after scores first, the first variable, before scores as a second variable. We look at options. Again, the default is a 95% confidence interval, so we'll just leave that as it is, and OK. So here's your output. There's your summary statistics with regard to each variable, after scores and the before scores. And you also have the correlation coefficient. Now remember, we said that the paired procedure is useful if there's a positive correlation between the variables. There is here, but it's not very strong. It's fairly weak, this correlation, but nevertheless we'll continue with the analysis. So here's some statistics for the test. So here's your mean, standard deviation, standard error, and your confidence intervals for the difference now, and your t-test statistic with its p-value. That's a p-value for the two-tail test. So let's go to the notes and discuss the test there. So that's just showing you the dialog boxes in order to get the outcome for the paired sample test. And there's the output here. So what we'll do is we'll let mu d be the mean difference between the after and before scores. Then in that case, in order to test whether there's been an improvement after the skills test, then we look at H1 mu d being greater than 0. So the null hypothesis is mu d being less than or equal to 0. So our test statistic is given there, 7.495, 39 degrees of freedom. And since we have a one-tail test, we're going to make sure that our p-value is for one-tail. In this case, it doesn't make any difference because the p-value for the two-tail is also 0. So the decision would be to reject H0 if the p-value is less than 0.05, and clearly it is. And for any reasonable level of significance, we would reject H0. So the sample data does support the claim that the organization's training program is increasing new employees' working knowledge of computing. That's fairly straightforward. I could ask you to explain how that test statistic has been obtained. So you'll have to think about, well, we've got the mean of the differences, we've got the standard deviation of the differences, we know the sample size. How do we arrive at that test statistic? The formula that we have for that test statistic. The confidence intervals we can see are given here, the difference between the pre and the post and the pre-training scores. There's your upper and lower limits. So we get between those two values there. So we estimate that the mean difference in scores would lie between 9.345 and 16.255. What's interesting here is that the entire interval ranges over only positive values. So this would indicate that the organization's training program is probably increasing the new employees' working knowledge of computing, because we're looking at all of the differences being between a smaller positive value and a larger positive value. If there was a 0 in between, then of course we'd conclude that there'd be no difference in the scores before and after the skills program or the training program. In order to be able to make use of this testing procedure, the difference between the random variables d is assumed to be normal. So we can check for this, but in order to do that, we first have to calculate the difference between these variables, difference in the values between these variables. So we make use of this procedure, transform compute variables. So let's go back to SPSS. So transform compute variables. And what we want to compute here is a difference, so we'll call the target variable difference. And we want the difference between the after and the before scores. Okay. And that creates a new variable in the data editor screen. Okay, so here it is here. And if we go to the variable view, we can label it as a difference. And we really don't need those decimal places, so we can just go down to 0 there. So that's the variable view. Now back to the data view, and you can see here are your differences. So in order for us to determine whether the differences follow a norm, that's a population differences follow a normal distribution, we need to do the usual diagnostic checks. So we will go to Analyze, Descriptive Statistics, Explore, and this is what we're interested in, the difference. Make sure that that's highlighted there because we want both graphs, that is plots, and summary statistics. So the statistics, we have the confidence interval as before. Plots, we don't want the stem and leaf, we'll use the histogram. The box plots are generated as well, and we want the normal probability plot. So let's go to obtaining this, and we can have a look at this. We can see here that the median and the mean, very small difference between the two. The trimmed mean and the mean are almost the same, just in the decimal places here. So that implies there's probably no extreme values. The fact that the median is close to the mean implies that our distribution could very well be close to being symmetrical. Well, here we have it, and we can see here that it's really not all that much skewed. If we were to superimpose a normal curve, it'll fit quite nicely. If you look at the QQ plot, most of the points are along the axis. If you're a little bit away, but not serious. And if we look at the box plot, there are no outliers, no extreme values. So if we go back to what we have here, it's just describing what we've been doing. And we can see that even the skewness and kurtosis are within their respective two standard error, plus or minus two standard error bands, implying that the underlying distribution of differences is normal. So we can conclude here that the assumption of normality is in fact valid. So this was pretty straightforward. There were no extreme values to remove, no outliers to remove, and clearly from here, from the skewness and kurtosis, the implication that the distribution is in fact normal, and also from the normal QQ plot. Okay, we'll stop here. We'll continue with hypothesis testing for two populations in the next video.